Whenever you type a prompt into ChatGPT or ask an AI to generate an image, it feels like magic, right? Like it's just happening out there in the invisible cloud.
Right, but the physical reality of that request is anything but invisible. I mean, somewhere in a massive warehouse-sized data center, you've got this incredibly hot, heavy brick of silicon.
Yeah, and it's just chugging through billions of calculations, drawing enough electricity to power a small neighborhood, honestly, and requiring, what, gallons of water just to keep from melting down.
Exactly. We tend to think of this whole AI revolution as a software phenomenon. But the undisputed king of this new world is actually a hardware manufacturer.
You mean NVIDIA?
NVIDIA, yeah. They are sitting on a 90% market share in the AI semiconductor space right now.
Which is just wild, 90%, with a valuation exceeding 600 trillion yen. From the outside, it looks like an absolute impenetrable fortress. Okay, let's unpack this. Because our mission today is to look at a stack of incredibly detailed sources we got our hands on.
Right. We've got translated Japanese technical interviews, architectural breakdowns, white papers.
Yeah, and these sources reveal a completely different future. We are diving into how a Japanese startup called Renzo plans to take on this 600 trillion yen Goliath. And their secret weapon isn't just a slightly faster chip.
No, not at all. It's a radical new AI architecture, designed by the very same engineering veterans who built the core processors for Sony's PlayStation and Fujitsu's supercomputers.
Which is quite the resume.
It really is. What's fascinating here is that this isn't a story about incremental improvements. This is a fundamental rethinking of how computers have been built for the last 30 years.
A complete paradigm shift.
Exactly. They are attempting to bypass the literal laws of computing physics. Because the reason Renzo even has a fighting chance here is that NVIDIA's massive fortress is built on a foundation that's actually beginning to crack.
Right, under the sheer weight of modern AI. I want to dig straight into that hidden weakness. To understand how a tiny startup could possibly challenge a behemoth, we have to look at the chips themselves.
The physical architecture.
Yeah, because according to our sources, despite being the most advanced hardware on the planet, NVIDIA's GPUs are fundamentally based on a remarkably old concept, the von Neumann architecture.
Right, John von Neumann. He came up with this conceptual model in the 1940s.
The 1940s?
Yeah, and it has powered almost every computer you've ever used since then. So in this architecture, you basically have two distinct physical locations on the chip.
Okay, lay it out for me.
So first, you have the memory. That holds all your data and the instructions for what to actually do with that data. And then physically separated from it, you have the processing unit.
The arithmetic logic unit, right, the part that actually does the math.
Exactly. So logically, to do any computation, those two separate physical areas have to communicate. The sources break this down into a 4-step fetch cycle for every single basic calculation.
A 4-step cycle, just to do one math problem.
Yeah. Let's say the processor wants to do simple addition. Step 1, the processor reaches out and fetches the instruction, like, hey, I need to add. Step 2, it fetches data A, let's say the number 5. Step 3, it fetches data B, number 10.
Okay, so it's gone back and forth 3 times already.
Right. And finally, step 4, it actually performs the calculation, gets 15, and then has to reach all the way back across the chip to write that result into storage.
Wow. So it's ping-ponging back and forth 4 separate times just to add 5 and 10.
Now take that 4-step ping pong and multiply it by the trillions of parameters in a modern large language model.
That is a staggering amount of traffic.
It's immense. Now, NVIDIA is incredibly smart, obviously. They don't just send a million individual requests back and forth like a standard desktop processor might.
Right, they use that trick mentioned in the breakdown, coalescing.
Yeah, coalescing.
Yeah.
It batches all these memory requests together so they can grab massive chunks of data all at once.
So it's like a master chef spending 60% of their energy just sprinting back and forth to the pantry instead of actually cooking.
That's a great way to put it.
Like, instead of walking to the pantry for salt, coming back to the stove, then walking back for a potato, the chef just carries a massive tray and grabs everything in one trip.
Right, which is certainly more efficient.
Yeah.
But the fundamental physical flaw is still there.
The chef is still walking.
Exactly. The chef is still spending a massive amount of time and energy just traversing between the stove and the pantry.
And at the microscopic scale of silicon, that walking requires an astonishing amount of energy, doesn't it?
It really does. Because wires on a microchip aren't perfect conductors. They have electrical resistance and capacitance.
So it takes actual power to push the signal through.
Yeah. When you push data down a wire, You are literally charging and discharging microscopic copper traces. That physical act of moving electrons generates heat and consumes electricity.
The sources provide a killer statistic here that really puts this into perspective.
Oh, the picojoules one. Yeah, share that.
So performing a single computational operation, like
Yeah.
actually crunching the numbers in the processor, takes about 20 picojoules of energy.
Right. 20 picojoules to do the actual thinking.
But taking that data and moving it just 1 millimeter across the silicon just to get it from the memory to the processor takes 26 picojoules.
Wait, really? It takes more energy to slide the data a millimeter across a microscopic wire than it does to do the complex math.
That is wild, right? But that's what the math says, 26 just to move it.
It is the unavoidable physics of capacitance. Because of this, over half of the massive power consumed by modern AI servers, I mean, the gigawatts of electricity these data centers are burning through it, isn't being used to calculate or think.
It's literally just being used to push data back and forth across microscopic wires.
Exactly. Engineers call this the power wall or the memory wall.
This totally changes how you look at the hardware market, you know? It explains why companies like SK Hynix and Samsung are making an absolute fortune right now.
Oh, selling high bandwidth memory. HBM.
Yeah, selling HBM to NVIDIA. Because if your main bottleneck is the distance and speed between the processor and the memory, your only brute force solution is to buy the widest, fastest, most wildly expensive memory available.
And physically stack it as close to the processor as humanly possible.
Right. And that brute force approach is why NVIDIA's chips are so expensive, power hungry, and run so incredibly hot. You are just throwing sheer electrical power at a structural inefficiency.
But if this memory wall is just basic physics, NVIDIA can't be the only one running into it.
Exactly. Surely someone with infinitely deep pockets has looked at this pantry sprint problem and tried to bypass it altogether.
Well, the sources point straight to Google for that, with their TPU, the tensor processing unit.
Right, the TPU. Google recognized this specific data movement bottleneck years ago, didn't they?
They did. They realized that if you were going to run global-scale AI, you cannot afford to waste 60% of your power just fetching data.
So what did they do?
They abandoned the von Neumann model entirely for these chips. They built the TPU around what's called a systolic array, which is a type of data flow architecture.
Okay, so how does data flow physically differ from the four-step ping pong we just talked about?
Well, instead of a processor constantly asking the memory to fetch data, a data flow model operates more like a waterfall.
A waterfall.
Yeah. The memory prearranges all the weights and parameters and pushes them continuously downwards through a massive grid of calculators.
Okay, I'm picturing it.
So the data just flows, like a continuous video stream cascading through the chip. And the mathematical operations happen simultaneously as the data passes through each node.
So there's no fetching.
No fetching, no asking, and no writing back to a central memory until the very end of the stream.
Okay, so going back to our analogy, the chef isn't walking to the pantry anymore. The ingredients are just rolling past on a continuous conveyor belt, and the chef chops them as they go by.
That is exactly it.
That sounds incredibly elegant. I mean, it solves the power problem and bypasses the memory wall almost completely.
It does.
But there has to be a catch, right? Because otherwise, every computer on Earth would just use systolic arrays.
You're right, there is a catch. The catch is extreme rigidity.
Rigidity? In what sense?
Because the physical wiring between all those calculators is permanently etched into the silicon to support that specific cascading waterfall. The TPU is a highly efficient one-trick pony.
Ah, I see.
It excels at exactly two operations, matrix addition and matrix multiplication. It is hardwired specifically to calculate tensors.
Which, to be fair, happens to be the exact mathematical foundation of the transformer algorithm.
Right. The architecture underlying ChatGPT, Gemini, and basically the entire current generative AI boom.
So it's brilliant for the specific type of AI the world is obsessed with today.
It is. But if you want a TPU to execute complex branching logic or, run a database or handle an algorithm that doesn't rely purely on matrix multiplication, it's virtually useless.
Just a paperweight. I'm looking at our sources, though, and there's an interesting tension here. Google has recently started releasing these TPUs to outside customers via their cloud services.
Yeah, they aren't just hoarding them for internal projects anymore.
Right. So if I'm Renzo, a tiny startup trying to launch a new low-power architecture, doesn't an apex predator like Google offering a cheap, power-efficient alternative completely validate the market and simultaneously crush my chances?
You'd think so.
I mean, why would anyone buy from a startup when Google is offering data flow chips?
You'd think the presence of Google would close the door on a startup. But from a strategic standpoint, it actually does the exact opposite. Google's move is a massive tailwind for alternative architectures like Renzo's.
Wait, I don't follow. How does competing against Google help them?
Because the biggest hurdle for any hardware startup isn't the technology, it's the psychological block of the market.
The mental monopoly.
Yes. For years, the default assumption in tech has been that to do serious AI, you must buy NVIDIA. You know the old saying, nobody gets fired for buying IBM. Now it's nobody gets fired for buying NVIDIA.
Right. It's the safe bet.
But Google, offering an alternative and proving that a non-NVIDIA architecture can successfully run state-of-the-art models at scale well, that shatters the illusion.
It proves to developers and investors that alternative architectures are viable.
Exactly. Google took the risk of kicking the door open, and now the entire ecosystem is realizing they aren't trapped in the NVIDIA ecosystem forever.
So they broke the mental monopoly. Google proved that data flow architecture is highly efficient, but their rigid, hardwired systolic array lacks the flexibility needed in a fast-moving research environment.
And that specific gap, the space between von Neumann's flexibility and Google's efficiency, that creates the exact opening for Renzo.
Okay, let's dive into this startup, starting with the team.
Yeah.
Because they are not messing around.
The pedigree here is serious. So, Renzo was founded by Kenma Fujiwara. He developed the core silicon for Sony's PlayStation 2 and PlayStation 3.
Wow. If you know anything about the cell processor in the PS3, you know Fujiwara understands highly complex, unconventional chip architectures.
Oh, absolutely. And his co-founder is Yasuhiko Nakajima. He's a former Fujitsu supercomputer developer and a professor at the Nara Institute of Science and Technology.
These are engineers who have spent their entire career squeezing absolute maximum performance out of silicon heat constraints.
Without a doubt.
Yeah.
And what they've built is called CGLA, Coarse-Grained Linear Array.
CGLA. And they are taking this seriously. The sources note they've actually contracted TSMC, the world's leading semiconductor foundry, to fabricate a 5mm square prototype of this chip.
Yeah, they're already making the physical silicon.
So how does CGLA physically operate compared to, the von Neumann ping pong or the Google waterfall?
It attempts to take the best of both worlds, really. Like Google's TPU, CGLA completely abandons the von Neumann memory fetch cycle.
Okay, so no sprinting to the pantry.
Right. But instead of a rigid two-dimensional waterfall grid, CGLA lines up its processing elements linearly. It utilizes what they call a self-updating data method, passing data along a single line, much like a bucket brigade.
Okay, a bucket brigade. So processing node A receives the data, performs its specific calculation, and instead of sending the result back to central memory, it just hands the bucket directly to processing node B.
Exactly. And then B does the next step, and so on. No one is sprinting back to the pantry.
Because the processing element itself holds and updates the data before instantly passing it to its immediate physical neighbor.
Right. And because they are neighbors, the electrical distance the data travels is reduced to microscopic fractions of a millimeter.
Slashing the capacitance penalty.
Exactly. By eliminating the high capacitance journey back to central memory, Renzo claims they can cut power consumption by up to 90% compared to traditional GPUs.
90%? I mean, when you extrapolate that across an industry that is currently trying to secure literal nuclear power plants just to keep its data centers running, a 90% reduction in power consumption is industry altering.
It's massive.
But how do they avoid the TPU trap? If it's a bucket brigade, how does it stay flexible enough to run anything other than standard transformer models?
That is where the coarse-grained part of CGLA comes in.
Yeah.
You have to understand how we normally achieve flexibility in hardware.
Okay, break it down.
So you have traditional CPUs, which are fully flexible but very power-hungry. Then you have FPGAs, field programmable gate arrays.
Right.
FPGAs allow you to rewire the chip at the level of individual logic gates. So they're highly flexible, but wiring things at the bit level is incredibly slow and inefficient.
Right. You're essentially micromanaging every single electron's path.
Exactly. CGLA takes a different approach. It maintains its flexibility at the function block level, the coarse-grained level.
So what does that look like physically?
The chip has physical switches and multiplexers built into the silicon between the processing nodes. So through software control signals, the route the buckets take and the specific operations each person in the brigade performs can be dynamically reconfigured on the fly.
Here's where it gets really interesting. Because the AI world refuses to stand still.
No, it moves insanely fast.
Right now, Every dollar of investment is flowing into transformers. But the sources highlight that completely new AI algorithms architectures with names like Mamba, Jamba, and XLSTM, they are already showing immense promise as potential successors.
Yeah. They handle memory and sequence length far more efficiently than transformers do.
And if the entire industry pivots to Mamba next year, what happens to all those Google TPUs that have matrix multiplication permanently etched into their silicon?
Like we said, they become highly efficient paperweights. They cannot run the new math.
But Renzo's CGLA doesn't need to be replaced. You don't have to rip the silicon out of the server rack.
Nope. The software simply sends a new control signal to the chip, flipping those physical switches, and the bucket brigade instantly reorganizes its routing to perfectly match the logic of Mamba.
It's like a physical manufacturing assembly line that can instantly reorganize its conveyor belts and robotic arms to build cars today and airplanes tomorrow without having to tear down the factory.
That is the holy grail they are chasing. You get the staggering power efficiency of a data flow model, combined with the future-proof flexibility of a programmable chip.
Okay, I'm completely sold on the physics. You have a chip architecture that bypasses the memory wall, uses 90% less power, dynamically adapts to future algorithms, and is designed by engineers with a track record of delivering world-class silicon.
It sounds perfect, right?
It does. So the million-dollar question for the listener is, why isn't Renzo an overnight success? Why isn't OpenAI or Microsoft throwing billions of dollars at them to replace NVIDIA right this second?
If we connect this to the bigger picture, it reveals a brutal truth about the semiconductor industry. Technological superiority, particularly in hardware physics, absolutely does not guarantee business victory.
Because there is an invisible barrier protecting NVIDIA.
A massive one.
And according to the sources, NVIDIA's true moat, the real reason their 600 trillion yen fortress is impenetrable, has nothing to do with hardware or the von Neumann architecture. It's entirely about software.
Specifically, an ecosystem called CUD.
Right, CUD.
CDA is the proprietary software platform NVIDIA has been developing for over 15 years. It is the translation layer that allows high-level code written by humans to execute flawlessly on the parallel processors of an NVIDIA GPU.
The sources make this sound almost like a religious devotion among programmers. I mean, for an AI developer, CUDA is the air they breathe.
Think about the actual workflow of an AI researcher. They're building models in Python using frameworks like PyTorch or TensorFlow.
Okay.
When they want to run their massive mathematical model on the hardware, they simply type a single command, device equals CUDA. That's it.
That one little line of code.
That one command hooks into millions of lines of optimized libraries that NVIDIA has spent over a decade perfecting. It seamlessly translates the researcher's abstract ideas into the specific physical gate operations required by the chip.
And because Renzo's CGLA is a completely different paradigm, because it operates as a self-updating bucket brigade rather than a traditional chip with a standard instruction set, I'm assuming you can't just type device equals CUDA and expect it to work.
Oh, it fails completely. CGLA lacks a traditional instruction set architecture entirely.
So what happens?
Well, when you move to a data flow model, the burden of figuring out how to map the math onto the hardware shifts entirely to the software compiler.
The compiler has to do all the heavy lifting.
Yes. The compiler has to look at the PyTorch code and translate it into a highly complex physical routing map that tells the CGLA switches exactly how to organize the bucket brigade for maximum efficiency.
Which requires an astronomical amount of engineering effort. So even if Renzo builds a physical marvel of silicon that uses a fraction of the electricity, if they cannot provide a software compiler that effortlessly translates standard Python code into a bucket brigade map, no developer will ever use it.
Exactly. Researchers aren't going to spend 6 months rewriting their code base in low-level assembly language just to save on their electricity bill.
And this is the immense challenge for any AI hardware startup. You aren't just competing against NVIDIA's hardware engineers. You have to instantly replicate a software ecosystem that took NVIDIA 15 years and thousands of developers to build.
Right. Without an easy, seamless software bridge, the market simply won't adopt the chip. User inertia is historically much, much harder to overcome than the physical engineering challenges of moving electrons.
So what does this all mean for Renzo? It means they have brilliantly engineered the world's most power-efficient, adaptable bullet train capable of bypassing the traffic jams of traditional computing. But NVIDIA currently owns every piece of track, every train station, and the entire ticketing system the world relies on.
That's a painful reality for a hardware startup.
Renzo doesn't just have to sell their train. They have to convince an entire industry of comfortable commuters to build a completely new railway network just to experience the ride.
Building the hardware was actually the easy part. The battle for the future of AI computing is going to be fought entirely in the compiler software.
For those of you listening, step back and look at the massive shift we've uncovered today. We started by looking at a financial monopoly, assuming NVIDIA's dominance was an unstoppable force.
But beneath the hype, we found a very real, very physical vulnerability.
Exactly. The power wall. And the sheer thermodynamic cost of sprinting back and forth to fetch data on an aging von Neumann architecture. We saw how Google brute-forced a solution with a rigid, one-trick data flow waterfall.
And we explored how a team of Japanese engineering veterans is attempting to completely rewire the physics of AI with CGLA. This raises an important question, though, as we look toward the horizon. AI models are not getting smaller. They're growing exponentially, demanding massive new data centers that strain the electrical grids of entire nations.
The physical limits of heat and capacitance on von Neumann chips will soon become financially and environmentally unsustainable.
Right. So will the eventual breaking of NVIDIA's software monopoly be driven by some brilliant new compiler innovation from a startup like Renzo?
Or will the industry be violently forced to abandon its comfortable software habits simply because the unforgiving laws of thermodynamics leave them with absolutely no other choice?
It's going to be fascinating to watch.
That is a phenomenal thought to leave on, because at the end of the day, no matter how elegant your software ecosystem is, you cannot code your way out of a melted server rack. The physical reality always gets the final say. Thank you for joining us on this deep dive into the absolute cutting edge of hardware physics. Keep questioning the architectures running the world around you, and we'll catch you on the next one.